controversial in the talk, I promise.
Oh, we wish that we would have some fight, no?
Well, it depends. Yeah, possibly.
Okay, should we start now?
Sure, I'm ready to go whenever you are.
Okay, so hello everyone. Good morning, good afternoon, good evening, depending on the part of the world you are now. I would like to welcome you to the Heliophysics and Space Geophysics seminars promoted by the Brazilian National Institute for Space Research, INPE. In particular, this seminar is being hosted by the Space Geophysics postgraduate program in our institute and by a project called Research in Heliophysics, which is a part of the internationalization effort going on in our institute, funded by our CAPES funding agency. Our guest today is Dr. Scott McIntosh, the Deputy Director of the National Center for Atmospheric Research, NCAR. Until 2019, he was the director of the High Altitude Observatory. He received his first class honor degree in mathematics and physics and his PhD in astrophysics from the University of Glasgow, Scotland. His research in the field of solar physics has focused on three main areas: the detection and impact of magnetohydrodynamic waves, the detection and understanding of ultraviolet and extreme ultraviolet radiation, and understanding the decadal evolution of the solar plasma. Dr. McIntosh has authored or co-authored over 100 journals, articles, and his work has been cited approximately 4,000 times. On behalf of INPE, I would like to thank Dr. McIntosh for accepting our invitation to present this seminar on magnetic Rossby waves in the sun and their influences on the solar cycle and the space weather. Thank you very much. We ask the audience to mute their microphones during the presentation. You can ask questions at the end, or if you prefer, you can write your question down at the chat. You can read the question at the end, or if you prefer, myself or our student, Adriane Barbosa, will read it for you, okay? So it's all yours, Dr. McIntosh. Thank you very much.
Yeah, thank you. Thank you for the lovely introduction, and good morning, good evening, good afternoon. And after the talk, it's maybe good night because I'll put you to sleep. But I thank you for the invitation. Yesterday I was in Switzerland. Today I'm in Brazil. This is fantastic. Different topics, different talks. This is work that we largely did 4 or 5 years ago, but has seen a somewhat of a resurgence, which is kind of fitting with the end of the solar cycle being near. And so I have a lot to get through, a lot of observations, a little bit of simulations that have been conducted by some of my colleagues, and possibly if I can get through it fast enough and clear enough, a kind of preview of what may be to come. And I got approval from Luis to do that bit, because it's not really to do with Rossby waves, but it's definitely connected, I think. Anyway, so I talk about magnetized Rossby waves in the solar atmosphere, or more generally global scale wave activity in the solar atmosphere, but more likely I'm looking at things that are changing in the sun's interior and then subsequently driving changes in the exterior in the solar atmosphere. So I will try to remember how this works with Zoom. I'm failing. Okay, so preface. Because I don't know the breadth of the audience, I'm just going to throw you in at the deep end. And I'm going to show you a plot of the sunspot number, or the number of magnetized large magnetic concentrations on the sun's disk over the last 22 years, actually the last 24 years. And you'll notice, contrary to the projection that's often shown of sunspots, that curve is not actually terribly smooth. Superimposed on the nice, smooth, decadal kind of envelope that you can see is a quasi-periodic signature. And that quasi-periodic signature can often have departures that are of the same order of magnitude as the decadal scale envelope itself. Now, these are not artifacts of the Earth's orbit. They are not artifacts of the Jovian orbit. They are not artifacts of anything. What they are physical manifestations of how magnetic flux penetrates the sun's photosphere and creates sunspots. And so partly what we're going after in today's talk are, study the impacts of those surges. What do they mean radiatively? What do they mean in terms of eruptive phenomena such as flares and coronal mass ejections that can destroy infrastructure, and a few other things. And if I get there, I'm going to get into what those vertical dashed lines are that seem to be very arbitrarily drawn, yet they are not. So, second law of solar physics, solar flares are intrinsically unpredictable. The third law of solar physics is I question that second law. I don't believe they're intrinsically unpredictable. They may be on a day-to-day scale, but I don't believe they necessarily are on a sub-rotational scale, so less than a month, and possibly even on longer time scales. You can tell based on that previous plot when the sun may be active, and that's one of the things that we've been looking at and what motivates this work. And why am I saying that? Well, if you look at the history, the last 20, this isn't 24 years, but this is 16 years of flare data from RESI and the GOES satellites, and decompose it by hemisphere. So the legend says it all, I guess. Red basically is north, blue is south. You see that those quasi-periodic surges are not synchronized across the sun's equator. And what you basically see that over the course of about 6 to 9 months, the sun's flare productivity will increase by a factor of 2 and then subside. Okay, very obvious. The other thing that should be obvious, if solar cycle maximum is around 2001 to 2003, the actual peak in flaring activity comes after that. And that's actually a well-known observational effect called the Nevishev gap. But anyway, it's not widely known that the sun's hemispheres display these, what we've dubbed seasonal surges of magnetic activity. And why we call them seasonal is if in the context of the sun, if a solar cycle, a sunspot cycle is a year, then these variations are happening on a scale shorter than that year. In fact, the periodicity is around 11 months. Again, going back to the sunspots, our original premise when we did this work was that they appear to be driven by rotational instability. And what's basically going on, or what our earlier premise or hypothesis was, that the magnetized bands, the toroidal bands are embedded in a rotating fluid. And the rotating fluid itself creates pressure perturbations that basically make the magnetic field preferentially buoyant at different times of the cycle. And when we look more at flaring activity, and here's the butterfly diagram showing the radial component of the sun's magnetic field as a function of time taken at the central meridian over some 35 years. If I superimpose the lower energy C-class flares, you can see the clear correlation between magnetic flux and flare production. And this isn't a shock, and it shouldn't be a shock to anyone, because flares originate in magnetized regions. However, when we start to go to the more explosive events, you can start to see aspects of clustering, and that those flares don't necessarily occur at random. They seem to occur either with or during these surges in emerging magnetic flux. If I dial up by another order of magnitude in the flare scale and go to the X-class flares, that correspondence becomes absolutely clear. That X-class flares are uniquely positioned when the sun is surging in flux emergence. Now, if I did my job right, I've done a little job here of trying to illustrate that. And so this is only the last several years. And X flares are red dots in the lower part. M-class flares are blue dots, and C-class flares are green dots in this bottom. And I kind of apologize for any of you that happen to be red-green colorblind. I tend to use those colors a lot. But what we show here is the mapping of flare location by hemisphere on the same curve as the sunspot modulation. And so you get a good idea that there's a very, very strong correspondence between where the surge of magnetic flux emergence is taking place and the occurrence of flares. So in principle, if you can predict or understand what is producing those surges of flux emergence, you have a far better chance of understanding when major solar storms will occur. Same data is reflected in CMEs. And if I go back to Luis's old work, I think it's in the next slide, you see that the modulation, or actually, I must have skipped that one. I actually used to have a slide in here talking about how the total solar irradiance and spectral irradiance also varies on the same timescales. But I guess I must have taken it out. But anyway, so the current, this mode isn't peculiar to solar cycle 23 or 24. In fact, you can see it through the entire time history of flaring activity. And in fact, in earlier times, it may have been significantly stronger. And over the last 3 solar cycles, the envelope of activity has actually been decreasing, which is another interesting tale for another day. And so I'm going to take a little bit of an aside, and maybe there's some meteorologists on here, maybe not. They were probably put off by the title, but I'm going to talk a little bit about Rossby waves and illustrate them with this beautiful simulation from the from NASA Goddard Space Flight Center. And you may or may not know that Rossby waves are global scale modes that are the result of the Earth's rotation and the variation in the Coriolis force with latitude. Those waves interact with mean winds in the atmosphere to create jet streams that you can see beautifully illustrated in these plots. And to all intents and purposes, the pressure imbalance that are created by those waves drive local scale weather across our planet. They transport cold air from high to mid latitudes and create cold outbreaks. They are responsible and vice versa for droughts. And so all of our stormy weather activity is driven largely by this rotationally driven phenomena. So the restoring force, as I said, the restoring force for Rossby waves is the Coriolis force. They originate from the Coriolis force in a rotating shell because our outer atmosphere is relatively thin. Now, the interesting thing, as you know, because you guys live in the southern hemisphere to some large, mostly, the Coriolis force tends to push things in different directions in both hemispheres of the Earth. And so what that basically means is that the restoring force is actually perpendicular to the direction of the flow, which creates some rather interesting phenomena. And if you're interested in getting into the theory in the nuts and bolts, I point you to a paper that was just published only a month ago, part of the American Geophysical Union Space Weather Grand Challenge series, as my colleague and I started to look at how to use these wave phenomena as diagnostics for advanced space weather forecasting. Now, I've been very speculative in making that jump about rotational instabilities, and I'm going to go into why some of the observational evidence I think that supports this. And so in 2011, about the start of 2011, we were lucky enough that between the Solar Dynamics Observatory and the two stereo spacecraft, we were able to image the entire solar atmosphere for the first time in human history. And those data continued for about 4.5 years before we lost stereo B. And they're still trying to recover stereo B. So I'm going to show you some of those. And the movies themselves are quite staggering when you stack the data together. Bear in mind, please, that typically the typical vision of the solar atmosphere is one where we only look at the part of the sun that is on the Sun-Earth line. And so I've taken a rather unconventional approach here and had a fixed rotational grid and put the data on in terms of their actual physical longitude on the sun. And so in this movie, you should be able to see precession of, if objects in this movie were stationary, they wouldn't move. And so you see a precession of phenomena slowly drifting to the right, but also features that are drifting to the left. But, so getting into this data is rather complex. What I did was quite so obvious from that movie, but when you look at these features, images individually, the sun is covered in these very small magnetic dipolar regions that we cunningly call magnetic coronal extreme ultraviolet bright points, because they're seen in the ultraviolet and they're bright and they're small, because the physicists are very creative in their descriptive capabilities. But what we know is that these features are ubiquitous. They're also separated in papers that we wrote a good part of 8 or 9 years ago, illustrated that these features are not random. They're not just randomly formed by convection, and that the large majority of them seem to reflect underlying global scale motions. And so you can learn a lot by tracking them. And so I'm going to show a different perspective of the 3 different spacecraft as a function of time using these bright points. So every one of these dots in this image comes from the separate spacecraft. And you can see that as the stereo spacecraft separate in time, we begin to obtain this full global coverage. And you can start to see the fact that there are clusters of magnetized activity. Probably most striking is there's not much going on above 55 degrees latitude, which is interesting in itself, but there are predominantly hot longitudes. And by that, I mean longitudes where magnetic activity seems to be prevalent. Taking a slightly different look at that data and synthesizing, aggregating it over 28 days, you can make a PDF, a probability density function, to look at the migration of these magnetized features. Another one of my favorite tables here. But again, you get this idea that there's motion, that things are not stationary with longitude, and that there are significant drifts. Now, if I slice, because I have a 360-degree look, I can slice this data in any way I want. And so now, instead of scanning in time, I'm scanning in longitude. So I'm actually taking a rotational. So this is latitude versus time at different longitudes. And so you can see that at different longitudes, there are clusters of magnetic activity that are recurrent. Okay, so that's a thing to kind of get a hold of. Because I'm rather perverse when it comes to data analysis, I go a step further and I can turn these into polar projections. And you remember my earlier brief comment around the lack of these features above about 50, 55 degrees latitude. But you'll also notice now, compared to my opening slide, that the precession of these things, these magnetic clusters, is quite prevalent and also quite beautiful, and also not so dissimilar from the manifestation that we saw in the terrestrial simulation earlier. And so, you know, I'm going to apply a standard meteorological trick. And in fact, Carl Gustav Rossby used the same meteorological trick to understand the waves that then were given his name. And so this is called a Hofmöller diagram, named after the person that first constructed it, but it's basically longitude versus time at a fixed latitude. And so if I place a ring, an annulus, a thin annulus around a given latitude in my data, and then superimpose each longitude as a function of time, I get the plot on the right-hand side. And so this is now a space-time plot. And so gradients in space-time plots, of course, reflect speeds. If I show you in 3 different parts of the atmosphere, and I'm going to reference this again later, but I'm going to show you, you'll notice the mysterious horizontal band, but the longitudinal sampling, Hofmöller diagrams at 3 different regions. The leftmost one in the northern hemisphere centered on the activity bands of cycle 24, a narrow band around the equator, and then another band in the southern hemisphere. And you'll notice the distinct asymmetry in activity, but you'll also maybe notice that because of the inverted color scale, that something rather peculiar happens in the equator right about the same time that activity starts to kick off in the northern hemisphere. Very peculiar. But anyway, if I start to diagnose and analyze these little clusters that are in the Hofmöller diagrams of the northern and southern hemisphere, I get some very curious things. So the wave, what appears to be a motion, has a prograde phase speed, so the red line, of the order of 3 meters per second. So you're measuring a speed of 3 meters per second on an object like the sun. It's pretty staggering, and to do it by remote sensing is probably even more. But the wave, the clusters themselves seem to have a retrograde group speed of about 20 meters per second. So you see that there's 2 different motions present in the magnetized features that you see, both prograde and retrograde. So in the direction of rotation and against it. One of the other curious things that we see is that if we look at the lifetimes of the various clusters that we identify, so they basically apply a clustering algorithm to these small black patches, we see that their lifetimes appear to be integer numbers of the rotation rate of the atmosphere at given latitudes, which is very curious. And furthermore, that over the 4 years, there seems to be a particular preference for certain longitudes. And I don't want to go into this too much, but the longitudinal wave number, if you like, that seems to be preferred here is 1 of 5 or 6. But anyway, at times like solar minimum, like right now, it's usually 1, the longitudinal wave number. And so it turns out that these are characteristics of Rossby waves, and in particular of magnetized Rossby waves that have been studied in the literature, a great deal, but never identified. And they should also be differentiated from some colleagues from the Max Planck Society who discovered some equatorial hydrodynamic Rossby modes just a year or so after we published our paper. Those don't seem to interfere with the magnetic field, and they don't have the same characteristics. So there's something intrinsically different about these magnetized waves. So the question is, I guess, where are they? They're not in the sun's outer atmosphere. They're rooted somewhere in the sun's interior. And like the Earth's atmosphere, thin shells are important for the generation of these Rossby modes and the various jet streams, etc. And so my colleague Mosumi Dikpati at HAO decided to try and undertake studies of looking at the impact of a thin interface at the bottom of the sun's convection zone and the impacts of the Coriolis force on it. And what she identified basically was that the membrane oscillated. Let's see if I've got it. And I'm not going to show that. I'm going to show this. That the membrane itself at the bottom of the sun's convection zone oscillates. But it doesn't just oscillate in any particular way. It oscillates with prograde and retrograde motion. And I'll show you in a second the outcome of some of that. But basically, Mosumi is able to replicate, to some large degree, the emergence of magnetic field structures and then ergo the small dipolar regions that we see. One of the more interesting things, and this makes some intuitive sense, that as you drive the sun faster, so as the sun gets younger, that the rotational instability that is induced at the bottom of the sun's convection zone, possibly the seat of its toroidal magnetic flux systems, that the instability that it drives is actually increases and can increase several fold. So in other words, younger stars, faster rotating, possibly more activity. And that gets to a point where maybe the activity of this seasonal type scale is actually much significantly greater than any underlying decadal scale cycle, which is itself kind of interesting. And so I'm going to go back because there's another type of global scale wave present in this system. And I'm going to come back to the plot I showed just a couple of minutes ago. And at the bottom here, I've got a shaded region on the sunspot number to illustrate when this occurred. And in fact, if you look at these periodic surges present in the sunspot data, you can clearly identify the large flux emergence event that happened between August and January, August of 2011 and January of 2012, and reflected in the sunspot number. But this massive drop of flux emergence at the sun's equator systemically and then continued for the whole of the next year. So 3 things to note: rapid drop and change in flux emergence at the equator, rapid growth of flux emergence at mid-latitudes, and profound hemispheric asymmetry. So we started to look at this a little bit more detail using the same data. And what we noticed was that at some point in time, the sun rapidly transitioned from an m=1, a longitudinal wave number 1 state, into craziness, where many more than one longitude was active. Something was going on. And so I come back to this plot, an earlier work that we had conducted. And so right now, we're in this time frame, right? The right-hand side of this plot. We're in solar minimum, which means that the sun is largely unable to make sunspots. Not identically, but largely. And so one of the questions is, how does solar minimum end? solar minimum ends very abruptly. And if I show my UV bright point diagnostics again, you will see the same very abrupt change in magnetic conditions at the sun's equator in 2011 in this data set, as I showed in the previous one, which was the longitudinal sample. You'll also know the very rapid growth of magnetic flux emergence at mid-latitudes that resulted or happened concurrently. Just for illustration, I'm going to show a kind of conceptual, a data-driven conceptual mapping of the underlying magnetic activity cycle that underlies the sunspot modulation. So this is basically the sun's 22-year-long magnetic Hale cycle. And the vertical dashed lines seem to be the very ends of Hale cycles, which seem to be destroyed at the sun's equator. You may not care about this, but one of the things it does do is that the radiative environment of the sun changes in a veritable heartbeat. So in much less than one solar rotation, the sun's radiative output in coronal emission lines jumps up by at least 85%. So this is a star undergoing a global change in magnetic conditions in less than one solar rotation. And for those of you that study radiation, interesting aspect of this is that it's very much temperature dependent, and that as you go in range of temperature from around 100,000 degrees at the bottom of the plot on the left-hand side to the top, about 3 million degrees, and plot the ratio of before and after February 11th, 2011 in the data set, you see that there are a few percent jumps in coronal line emission, transition region and cooler emission up to about 1 million degrees. And above 1 million degrees, the change is quite profound with what looks like a Gaussian type envelope at the higher end of the spectrum, which indicates that the corona is extremely sensitive to changes in the underlying magnetic flux, but that's probably something we knew already. Longitudinally, I can take the same data set and apply a rotational time period to it. And I urge you to look and identify February 11th, 2011, where this longitudinal switch on of activity seems to have occurred. February 11th, 2011 isn't an isolated event. It is not a freak. A very similar event happened in September of 1997. And at the bottom of this, I show the solar radial flux from Canada, taken in Canada over that same time frame. And you see that there's basically a step function in the corona's radial signature at that time. One of the things we identified was that this is also the same time that the area of the sun's disk covered by spots finally goes above 100 microhemispheres. That's a very arbitrary number, but something that we noticed. And if you compare the historical record of F10.7, the 10.7 centimeter radial flux, you see these step functions are actually present in the last 60 years of data. So cycles 19 through 24 are not distinct. There is a single, almost soliton-like event happening at a point in time that basically is changing the sun's magnetic output. If I go back 140 years and I use the daily sunspot number, I show the plot on the upper side with the customary butterfly diagram on the bottom. So the positions of sunspots as a function of latitude and time. It's beautiful, right? This is Maunder's plot. But something very odd happens if you look at the observational record of what we call filaments or prominences. And these are eruptive structures typically, or not all eruptive, but they form at interfaces between oppositely signed magnetic systems. And so if I look at the time history over the entire time frame for which we've been taking photographic observations of the sun, so going back to 1860, and early work was conducted and published in 1903 and 1933, showing that the behavior of large, cool protuberances in the sun's outer atmosphere and tracked them. They noticed a very peculiar behavior that not only did they see the butterfly that had just been reported by Maunder, but they also noted a very peculiar behavior at high latitudes. And that was that once per cycle, there was an excursion from around 55 to 60 degree latitude towards the sun's poles. We later identified, of course, that is the start of the sun's polar reversal process. But what you'll notice here is that start of that polar reversal process at high latitudes is in the same location every single time as the derived change or death of the Hale cycle at the sun's equator. And so whatever is going on is not only driving the creation of sunspots, but it's modifying magnetic flux behavior also up near the polar regions. This is probably most best emphasized if I take away the density plot and just show you the highest latitude recorded filament in the system. Red is northern hemisphere, blue is the south. And you can see that things tend to want to stack at about 55 degrees latitude. And once per cycle, you see these curved protuberances that go towards the polar regions. It's very fascinating stuff. And so, again, charging my colleague to go and look at these, she came up with a hypothesis that what was happening, because it was happening on such a small timescale, that it was almost like a tsunami. And so this movie is greatly exaggerated, of course, because this is actually a very thin shell. But this is partly a simulation to illustrate conditions that as the magnetic pressure changes at the equator with the death of the Hale cycle, that change in the pressure environment is then communicated very rapidly by a magnetogravity wave, basically, throughout the sun's interior, which then changes thereafter the sun's magnetic flux emergence characteristics. And so I've come to probably the end, although I do have an end-to-end, but I'm going to go over this a little bit. So the sun exhibits seasons of activity. Those seasons are manifested in all solar proxies. Those seasons result in quasi-periodic surges in magnetic flux emergence, and global observations indicate the presence of magnetized Rossby waves in the sun's interior, which then drive the changes in the exterior. The waves likely or possibly occur at the bottom of the sun's convection zone, because the simulations we can conduct can replicate the latitudinal and longitudinal behavior. And for those of you that study space weather or are interested in forecasting space weather, it's probably the study of these types of wave motions that may present massive breakthroughs to the space weather paradigm, because if you can understand and or predict based on the waves that are being observed when the next surge is going to occur and at which longitude it's going to occur, just like terrestrial meteorology, your chances of nailing an M or an X class flare are dramatically higher than they were if you were just waiting for the sun to explode. On the tsunami, so the sun's 22-year Hale cycle, I've got on here but haven't shown you, is recurrent and robust. The magnetic bands of the Hale cycle have a definitive end, and for the lack of a better term, we call it the terminator just because it's end, but you can get into all kinds of fun comparisons with that. This terminator event that happens at the equator with the death of the Hale cycle can trigger growth of flux emergence at mid and high latitudes within only a short number of rotations, which is absolutely ridiculous. Likely, it's another type of global scale wave, but one that, just like the torsional, not the torsional oscillation, but the TNO, this Rossby-like motion in the tachocline, affects pressure balance. The difference is this one affects the global scale pressure balance, which makes us believe that it's a tsunami-like event. With the terminator, we see a rapid jump in solar proxies throughout the entire atmosphere. And one of the crazy things is, of course, is if you look at this plot, and this plot ends in 2022, you'll notice that the next terminator could occur anytime. And so for those of the that are studying data from the Parker Solar Probe or from the Solar Orbiter spacecraft, should be very excited about what may pass in the next couple of months. I do have a couple more slides, but I noticed that it's 45 minutes in. I'd like to talk a little bit now about what the work on these termination events can tell us about solar cycle 25. So if you recall from an earlier slide, I showed that the envelope of solar activity has been decreasing for the last 30 years. And up to a couple of years ago, I was fairly convinced that that was going to continue and that solar activity was going to wane away. But some work that was done about 12 months ago now significantly changed my mind. And so if I revert back to my plot here, and I revert back to my note that says that the sun's cycle is, magnetic cycle seems to be extremely robust and repetitive. And what I'm going to do is try to characterize the behavior of the sun's atmosphere in the context of these termination points. Okay. And so we wrote a paper about 18 months ago where we used a bunch of different diagnostics to identify proxies to identify the occurrence of these spots and these events. One of the complaints of the reviewers, and maybe rightly so, was we didn't have a very algorithmic approach. It was a quite subjective approach. And so they requested that we look at an algorithmic approach. And so develop a numerical algorithm to try and verify those subjective detections. So we're going to go in here and show you what we did. But basically, I'm going to jump a very long story short and say that Hilbert transforms are possibly man's best friend next to a dog. Because unlike a Fourier transform, a Hilbert transform allows you to understand phase transitions in time series and allows the phase to be non-constant with. And the sun almost always exhibits a non-stationary time series. And so if I show you plots of, again, the solar radial flux over the last 60 years, you'll notice two things when you apply a Hilbert transform to that data. One, the amplitude function in red peaks at a given time. And two, the phase function. So the variability of the phase in the time series with time flips at a certain time. And both of those times are the same. Interestingly enough, those are reflective of the maximum rate of change of the F10.7 time series, i.e. at the terminators, these jumps, these significant step functions. If I do the same analysis for the hemispheric sunspot number, I get very strong occurrence. In fact, the Hilbert transform-based method verifies our more ad hoc determination of terminators with an accuracy of about 3 months. So that's great, which means that we can verify our earlier work back to 1940, but that means we only have 14 cycles to go by. Now, one of the questions was, when does the next cycle appear? Or when does the next terminator end? And because of this semi-linear behavior of the phase function, we've done the simplest possible thing and extrapolated out here at the right to see when the phase function is going to wrap around. And this plot is now rather old because the window is now shrinking. And the projection is that it was last month or 4 months from now, which means that the time separation between the end of, or the start of cycle 24 and the start of cycle 25 will only be about 9.25 years. So much shorter than average. And how do I know that? Well, I'm going to use my same Hilbert transform approach, and I'm going to detect the phase transitions, and I'm going to catalog them as a function of time. But now, if I use the monthly sunspot number, I can go back much further in time. I can go back to 1750, and I can effectively double the number of sunspot cycles. And so the yellow diamonds here are the previously detected terminator times, and the red is the 12-month smooth sunspot number analysis, and the black dots are the actual monthly data. And what you see is very strong agreement. And your eye may also start to detect that when there's very low solar activity, like back here at the Dalton minimum in 1800, the termination events seem to become more separated in time. Whereas when there's increased activity, they seem to compress in time. And so there's two kind of experiments I want to form. One is comparing the peak sunspot productivity between two consecutive termination events, so the separation of them, and then the comparison with the strength of the upcoming cycle. And so I'm going to refer back to my schematic here, where I show the interleaving bands belong to the different sunspot cycles. And so one of the things that our hypothesis was that the interaction between these gross, large-scale magnetized bands actually helped to shape sunspot cycle, largely because of, one, the termination event, but two, this is solar minimum right here between 2007 and 2010. And you'll notice that there are 4 oppositely polarized magnetic bands at the equator, and the sun can't make spots. It can only make spots after the end of the termination. So if I make these two experiments, number 1 and number 2, I get the following plots. Number 1, terminator separation versus intermediate cycle strength, I get nothing. No predictability, no indication that there's any strong relationship there. However, if I compare the separation of the terminators versus the upcoming cycle strength, and I look at all the particular statistical variables, including the various prediction confidence levels, we see that cycle 25, should the terminator come sometime in the next few months, sunspot cycle 25 would cut through this line at about 250 spots. And to put that in context for you, the worldwide NOAA-NASA panel to evaluate the cycle of 25 using all manner of physical and numerical models came up with a number half as small, which presents us with a bit of a dilemma. However, we'll get there. Hale cycles overlap. The endpoint seems to be some kind of trigger. That trigger grossly manifests itself in changing the magnetic flux emergence characteristics across the sun. The corona responds very definitely. Hilbert transforms are incredible. We are thinking about the next cycle ending very soon, but that means that with pretty high confidence that the sunspot cycle 25 will be rather large. And I question actually as to whether we're ready for a large sunspot cycle. We're excited about the prospects of Orbiter and Parker flying through this event, this tsunami, because we also anticipate that the same tsunami should ripple through interplanetary space as the sun's magnetism changes. And of course, there's also the interesting point of how will the Earth's atmosphere respond. And just for fun, I'll show you that the hindcast using our relationship is actually remarkably good, but it under predicts large cycles. So our 250, 233 spots may actually be an under forecast of the magnitude of cycle 25, but only time will tell as to whether we're right or wrong. And so the conclusion, the final conclusions, and I thank you for your patience, and I'm sorry if we're not going to have terribly much time for questions, but if this terminator happens soon, all indications are that cycle 25 will be in the top 5 since records began. Their relationship underestimates big cycles. Terminators themselves provide fiducial clocks, possibly to understand the climatology of things like space weather and a whole host of other solar proxies. That because I think one of the issues is we've always used the sunspot cycle as our clock. But those who study the sun will tell you that the sun's sunspot cycle periodicity is not robust or very clean, varying from 8 to 14 years. So, but the terminators seem to be far more definitive, physically motivated start and end points for activity. So I'm actually fairly scared about a large sunspot cycle 25. I don't know how you feel. I'm fairly sure that we're not ready for that to occur. And with that, I am done. And thank you for your attention.
Oh, thank you very much, Dr. McIntosh. It was very nice, very interesting presentation. I will pass over to our postgraduate student, Adriane Barbosa, to handle the Q&A. Adriane, are you able to speak and listen?
Yes, can you hear me?
Yes, it's all yours.
I will apologize for the sheer volume of stuff there, Luis.
Oh, I'm sorry.
And Alison, I'll apologize for the volume of material I threw your way.
Oh, no problem. It was brilliant, interesting, very good. Thank you.
Okay.
Thank you for your talk. So to start the questions, before I start reading the chat questions, you can ask your own questions. Please use the raise hand before talking.
Okay, would you like me to read them out?
Yeah, Edmund, can you please do your question?
Yes, can you hear me?
Yes, I can, loud and clear.
Yes,
Hi, really interesting presentation, thank you. And thanks very much to everyone for posting this. There's loads of questions, but just one for me for now. In terms of your cycle 25 prediction, just in terms of the delta, which, like, you know, that's an astonishingly large prediction. And just wondering how that sits in terms of the past climatology of changes in peak to peak, effectively. Is that within the envelope? You know, your top 5 one makes me think it's probably quite an outlier.
So you're meaning if there was a small cycle, what's the probability of it jumping to so large?
Exactly.
I actually pretty good, because I believe, and maybe scholars will say that the cycle when we came out of the Maunder minimum, the cycle following the end of the Maunder minimum was actually very large, or fairly large. But that's going back before this record. I think it's. I was rather perturbed myself, but we had a good hint that it's probably not so abnormal. And if you know, I won't go back and show. I could. One of the issues we noticed is that there's some very peculiar behavior in the phase function of the Hilbert transform.
Mm-hmm.
And there may be a hint in that behavior as to why solar cycle 24 is so small rather than why 25 would be so large.
Okay.
That's
yep.
a little bit cryptic, but I don't think 25 is unusual. It's slightly larger than average.
Great, thank you.
Do you have another question?
I do, but I think I'll let everyone else ask theirs first. Okay, very quickly. Just if you're, so it sounds as though there's a solid theoretical underpinning for the magnetized Rossby waves. It was just,
Yes.
I'm at the Meteorological Institute at the Met Office, and we see a lot of these Hofmuller plots, often in the context of things like the Madden-Julian oscillation or things like that.
Yes.
I'm guessing that this is not applicable here, given the change between, you know, your m equals 1 and higher wave number ones, and that Rossby waves are a better contender. I was just wondering if you'd, if there was, like, you were alluded to a solid theoretical underpinning for it being magnetic Rossby waves, and I was wondering if you could, yeah, I guess some of the papers you brought up might link to that, or if you could just speak on
there's
quickly.
there's an AppJ paper that's actually just been published. So there's two papers. One is an AGU Grand Challenge paper talking about the application of the theory, the observations and theory towards the kind of pre-seasonal type forecasting of space weather.
Yep.
But there's a even more recent paper in AppJ about the theoretical underpinnings that goes way into the theory of MHD Rossby modes. So I point you to that one.
Great, I'll have a look. Thanks.
That's a whole separate presentation.
Thanks, that's it for me.
All right.
Okay, next question.
I'm Francisco from Rome to Vergata.
Sure.
Oh, hey, Francisco.
Hi, Scott. Recently, various papers claiming for a possible planetary synchronization of solar cycles appeared. So what is your opinion about this possibility to explain peculiar longitude related to the planetary positions?
All right. I think it's a function of energy density. That even though, and primarily they point to Jupiter, I think, in the gas giant. You know, it's funny because Stuart Jeffries brought that up with me a long time ago when we were looking at this. I don't know if you've talked to Stuart about this, but I think there's not, if you compare the energy density from the tidal forcing between Jupiter and the sun and the rotational energy density of the sun itself, they're orders of magnitude off. And so it may be, I mean, if it was the butterfly effect, that, you know, a small change or some small tidal pool has a significant effect on global flux emergence on the sun. You can't discount it, but the energy density seems to be so far off that it's hard to reconcile. Also, the fact that these termination events seem to have far more significance in establishing the sun's clock. They're not, these are like solitons. They're not periodic themselves. So I greatly doubt that it's anything to do with orbital dynamics, which is intrinsically periodic. If that answers your question.
Okay, yes, thank you. Thank you, Scott.
Okay, next question. I'm going to start reading the chat questions now. From Oladayo, how can someone access the Rossby wave data?
They email me. I'll give it to them. Yeah, by all means. If you find me online and drop me an email, I can give you the cube of data in about 6 or 7 different formats. If you want to play games with it, I encourage more people to play with it.
Sure. Next
it's
question.
only a few terabytes.
Just a little. Okay, next question from Abimael. Do these results show the degree of geoflectness?
Not really. Well, it depends. If you go back and remember the sunspot plot, or the peaks of sunspots, and that we showed that the M and X class flares typically occurred when these quasi-periodic oscillations, the Rossby modes, were strong. That when I show that to my colleagues in the US Air Force, they start to get excited about the possibility of understanding when the strongest events occur. Of course, they don't always face the Earth. So if you were to run in forecast mode and you could tell how the longitudinal wave number was going to evolve, then maybe you've got a better shot of establishing when a more geo-effective storm was going to hit. But that's all future research.
Okay. Now, next question from Stella. If the Rossby waves on the sun are related to, in some way to the Alphen waves?
It's interesting. It's a good question. And of course, one of the, at some level, the difference is the restoring force, right? So there's difference in the Coriolis force versus the attention force in the magnetic field itself. It is not to say that there probably aren't actually alphenic modes on that system. They just don't seem to change greatly the buoyancy of the magnetic field, so we don't really see them. They're probably there. But until we can figure out something to go and probe the deep interior, we wouldn't be able to detect them. But they're probably there.
Next question, also from Stella. Do Rossby waves impact on solar wind?
Yes. So one of the things I didn't show was when you look at, so the periodicities that I showed very early in the presentation, and flares and coronal mass ejections, etc., also manifest themselves in the sun's open flux. And so if you look at the time series of open flux on the disk, it also exhibits the same quasi-periodic behavior. So yes, it does impact the solar wind.
Okay, next questions from Oladayo. Can you please shed a little light on how Rossby waves can be used to probe space weather?
Yeah, it's simple. Well, relatively simple. The waves themselves produce magnetic flux regions that appear at specific latitudes. Their motion in longitude is very predictable. If you understand the wave number present, so the number of these flux eruptions that are going on, you have a far better chance of understanding if and when a given longitude is going to produce a flare or a coronal mass ejection that could then hit the Earth. So at the very most basic level, it gives you a chance to understand when an event may happen long before it ever does.
Okay, next question from Onienia. What's the impact of tactile climb on space environment?
Well, I mean, if you believe this stuff, if you believe the stuff I've been rambling on about for the last hour, the tachocline seems to be incredibly important in at least modulating the space environment, because all the space environment is largely controlled by the shape of the sun's magnetic field. And so both the light that we feel at the Earth and the particles that we, the light that we see and the particles that we feel are shaped by that magnetic field. So if the tachocline is greatly impacting that magnetic field, then it also impacts the space environment.
Good. Next questions. Are Rossby waves the same as planetary waves? If not, what is the difference between them?
That's a good question, but as far as I know, yes. The answer is yeah, and I think in some degrees the language is used differently. I mean, so like planetary scientists won't talk in the context of Rossby waves generally, although they see them in the atmosphere of Venus and Jupiter and Saturn, and they're just global scale modes that they think are driven by the restoring force. I think what you're looking at there is some scientific, what's the right word? Purity, because they say that Rossby waves are in the Earth's atmosphere. It's kind of like you can't call it a spicule unless you see it in H alpha. You know, my solar physics colleagues will smirk at that, but I think it's the same. They're basically the same waves.
Okay, thank you. Paulo, if you want to do your question, please, you can do it. No?
Yes, thank you, Adriana. Hi, Scott. Paulo Simões here from Maize. How's it going?
Good, Paulo. How are you?
No, not bad, considering, right? So a quick question. You said, so the terminator phase there, when it happens, you said something about a very short time scale within one rotation, right? So is that more like a emergence of a very large region, or is it just a whole bunch of smaller ones? Because the reason I'm asking, because the early 2011, we had that big after region with lots of big flares, the famous February 15 events. So did you check on that?
Yeah, so we were more focused on how the longitudinal wave number changes. So it goes from being, you know, one region to being many in a very, very short time scale. But it's highly likely that, you know, that it'll be the same as cycle 25. When the next terminator happens, we could have an absolute whopper to kick off the event, right? Or to kick off the cycle.
Yeah.
So honestly, Paulo, I haven't looked at the size distribution.
Okay, so it's worth to check because, you know, I'm a flare person. I'm waiting for flares.
Yeah. You're a flare person.
Yeah, I am. Okay, so it's worth checking what happened in 2011, early 2011 to see.
Yeah. I mean, there is a fairly huge region in the north that emerged right after that event.
Yeah.
But then that doesn't help you explain what happened at the equator.
No, definitely not. I agree. Yeah.
Right. So the equator just went dead.
Yes. Yes, it did. That's quite interesting. Thank you. Thank you, Scott.
Yep. No problem.
Okay. Next question. How do the Rossby waves affect the planet's weather and climate?
Sorry, can you repeat that again? Sorry.
It's from the questions before that I read. They asked if the Rossby waves are the same of the planetary waves, and you said basically yes. So they asked how it affects the planet's weather and climate.
Oh, climate. I'm not going to touch climate, but I'll go for weather. I think that the idea here is, as I said early on, that those global scale perturbations in the pressure balance of the Earth's atmosphere, as we know from the laws of thermodynamics, pressure changes drive winds. And so when you have these pressure imbalances at the convective scale, it then changes the wind structure, which then basically modifies clouds and modifies weather. So, I am not a meteorologist. Maybe my friend from the Met office can tell me if I'm talking absolute garbage or not. So,
No, I think it's roughly right. I mean, just to say that for us at the mid latitudes, kind of especially over the UK, these this change in the jet stream that can be induced by can really change our weather patterns, whether we have stable conditions or whether it's kind of it's quite rainy at the moment, which is a bit more normal.
Right. And yeah, right. And where those nulls sit is very important. The peaks and troughs of the jet stream pattern. So
precisely.
And you don't want to be locked. I don't know. I don't want to touch climate.
Okay. Next question from Luis Eduardo. What does synchronize the hemispherical activity?
Great question. I have my own personal feelings on that, but I don't have any concrete proof. I like the wave that Paulo was discussing, this termination event. If it's really some kind of tsunami, a tsunami is a soliton pressure pulse. I actually have the feeling that the interior itself is moderated by internal gravity modes. So basically, like the Earth's scale convection is maintained or through a process that they call teleconnection. And it's basically gravity waves that talk to the large scale convection cells. And so I think that a similar phenomenon is happening on the sun, which then loosely regulates these magnetoacoustic gravity waves, basically regulate very quickly the behavior in each hemisphere, but it's still pretty loose. But if you look at that termination event, that's probably the most catastrophic form of global scale connection. But the fact that you have things like solar minimum, where you have 4 bands inside 45 degrees of the equator, indicates that those bands are interacting with one another at some level. I don't know the process, but they must be.
Okay.
And then there's a second question. Is it possible to assume some variability of the heat flux at the bottom of the convection zone? Yes. That's an interesting one. There's been a few papers talking about gradients between the equator and the pole, which produce winds, which probably maybe even results in meridional circulation. There probably are gradients, but I think the convection zone itself tries to isotropize, if that's even a word, what's going on. And I'm certainly no convection expert, but I think it's hard, unless you have some systemic gradient, a difference between the polar interior and the equatorial interior, then I don't know. I think it's a good question, but I can't tell you the answer.
Okay. Next question from Ligia. Rossby waves breaking in an important mechanism in Earth's atmosphere, which provides a two-way exchange of air between the tropical upper troposphere and lower stratosphere, and the lower stratosphere. Does the magnetic Rossby waves also break in the sun?
All right, so you can imagine interesting phenomena here where the actual emergence of a bipolar active region could be like the breaking of a Rossby mode, right? Like a sudden stratospheric warming. You could take yourself to the conclusion that the breaking of the wave is very much like the emergence of the sunspot itself. So yes, in other words.
Okay, now a question from Brennan. What is the relationship between latitudinal propagations of the waves and the butterfly diagram structure? And the next question also from Breno. What is the effect of toroidal field cyclic reversal on Rossby waves? How does it relate to hemispheric asymmetry?
Oh, sorry, I muted myself. The first question is latitudinal propagation. So those are, that's the butterfly mechanism itself. I'm very out on a limb with that one in terms of what I think's going on. And I think there's a significant breakdown in, or it doesn't even apply. There's an approximation that's made in dynamo theory called the thin flux tube approximation, or the frozen in approximation, where the implication is that the magnetic fields are very small, weak, compared to the motions that they're embedded in. And I'm not entirely sure that that's the case. And so the first question there is different kind of wave. And it may not even wave. It could just be induced electromotive force between the two. So I won't go into that any further. But the second one, polar field reversal, I don't think the polarity matters. It's only the strength. And so you'll only see changes in the Rossby mode signature with changes in the strength of the field and not necessarily the polarity. I think it's completely ambivalent to polarity of the field.
Okay. Next question from Sampda. Could you please suggest any solar instrument we can establish at universe free of cost for an early career researcher?
Yeah, like the one I have here. I have a small Coronado solar telescope. They're only a few $100s. You can buy them online fairly easily. If you want to go to higher end stuff, you can go and get some of the Mead stuff that's readily available. That's maybe, you know, an order of magnitude more expensive, but you know, those are good places to look. The Coronado H alpha cameras are very good, and I think now you can buy calcium ones too. So those are very good for doing some preliminary poking around with solar activity on the cheap.
Good. Next from Edmund. Realize the set short time scales. Is there any observational data set which might capture this?
Wow. So we're basically trying to use the tsunami concept to explain why the rapid change at the equator can be communicated so quickly to 35 and 55 degrees latitude in almost no time, right? Convection is an order of magnitude too slow to carry it, so it's not sound waves. If it was an alphanic wave, so a magnetic field wave, the magnetic field strength would have to be in the range of megagauss. I'm not sure that there are several megagauss. I'm not sure that that's the key. And so we started to look at things like magneto-acoustic gravity modes. And they actually can replicate the same changes, or the propagation that you would need to explain how the sun varies over 140 years. I don't know if that answers your question, Edwin. The change in solar conditions is so rapid,
yeah,
but it's very precise.
Yeah, no, it's just wondering, because it's a it's a nice explanation of the gap. Like, what is the mechanism that could fill this gap? And it sounds like it. And it's just wondering if you can get some observational evidence to support that. And I guess the corollary to that question is, where is the modeling placing this tsunami? Is that in the solar atmosphere, or is it in the solar interior? Just as in, like, what might be able to observe it.
Well, as it stands, it's down in that tachocline region again. I don't know if it's just because it's the particular favorite area of my colleague, but it's one of those places where it's another one of these crazy interface regions. And so basically the physical parameters kind of work there. I doubt it's not in the outer atmosphere. If it was, we would see it more profoundly.
All right. And
it's kind of like Nessie, right? It's Nessie. Nessie's throwing a tantrum at the bottom of the loch.
Right. Yeah. And it's just wondering if it's. I'm not at all familiar with the helioseismology data sets, but whether that has a high enough cadence to be able to capture anything like this.
Well, they've seen the other oscillations for quite some time, and they've attributed them to be QBOs. But the problem with helioseismology is and apologies to any helioseismologists left on, is they grossly average their data. Right. So they can have very high cadence data, but they have to average it over very long timescales to be able to extract physical information. So, I mean, I think it's very likely that when the next one occurs, we can do a much more detailed study with HMI on the Solar Dynamics Observatory to try and see if we see any signatures. I would be shocked if they didn't, but you can never tell. It depends on the windowing you apply to the helioseismic analysis.
Very interesting, thanks.
Okay, next questions. Matthew, if you want to speak, please do your question.
Yes, thank you, because I didn't know how to make it short. So thank you for the very nice presentation. I like very much these results. Shown. I have a question about filament, actually. So my first question is, where do you have your data from? Which data set is that? And the second one is about the signature of the rush to the pole that we can see from the filament. For me, the rush to the pole was linked to one polarity going to meet the other polarity at the pole. But at the same time, the filaments are usually on the inversion polarity line. So I don't really understand how you can have filaments going to the pole and then coming with their both polarity. So I don't know if you have thought about that and could clarify it to me. Thank you.
Yeah, thank you. No, I mean, you're right. Filaments trace out neutral lines. And that filament, that last high latitude filament, is absolutely tracing the interface between the excursion of the low latitude field into the polar cell. Right? So basically, we're using the filaments as a proxy to understand where the magnetic neutral line is. Right?
Yes, thank you.
Yeah, so that's exactly what we're doing. The kind of really unusual thing is, and until we looked at the data, we couldn't believe how synchronized the rush to the poles was. So the start of that polar reversal process was. I don't think, I certainly couldn't find it in any literature.
No, indeed. I was looking at some filament data and just noticed that. But so where do you have your data from?
So the data is a combination of from Archetri, Moudon, and Kanzelheuer, and where else? Somewhere in Russia.
Okay, I was looking at Moudon.
Kozlovsk. Okay. Yeah, in the Moudon data, it's interesting if you go back and look at the early papers. There's the guys from Archetri published in 1933. And Lockyer published some data from Q in 1903, and they already identified these patterns.
Okay.
So, and Moudon, the data was published in 1975, I guess, the first kind of systematic analysis of the catalog. So it's very interesting if you go back in and look at it.
Thank you very much.
So I just learned that Dr. McIntosh has another appointment now, right? Is that correct? So
yes.
My proposal is that we will record the questions that are remaining and send it to you directly so you can reply to them. So we
absolutely
deeply apologize to those who did not have their questions read or answered here. We promise we will take care of it. And with that, I would like to say that on behalf of INPE, on the Space Geophysics Postgraduate Program of our institute and the Research in Heliophysics project we have going on, I would like to thank Dr. McIntosh for this brilliant talk and this very interesting topic. Thank you very much.
Yeah, and thank you all for bearing with me, and good luck with all your future projects down there. It's very exciting what you're growing. So I watch with great interest.
Oh, thank you very much. I hope next time you'll come to visit us.
I hope so. I can't wait.
So I think that we can close. Thank you very much again to all the attendees.
All right. Okay, thanks, Luis, and thank you again for the invite. And I'll be in touch. I'll look forward to answering the rest of the questions.
No, okay. Bye.
Cheers. Bye, everyone. Thank you.
Cheers. Thank you.